Hello everyone and welcome back. Okay, so here we are at this very frightening example. You're like, why is it so frightening? Well, you're going to see soon. So what we have is a rigid steel bar. Whenever we hear rigid, it means that bar does not change shape. It does not deform at all. And supported by 3 rods. Notice not rigid rods. They can stretch, as shown in this figure right here. Now there is no strain in the rods before this load P is applied. After load P is applied, we can see the normal strain in rod 2 is 1080 microstrains. We're going to assume the initial lengths of L1 equals 130 inches, so that's the same for both rods on the sides, and 75 inches for the shorter rod. Now, it wants to find first what's the normal strain in rods 1. Okay, these are the same, so they'll have identical answers. But then here's where things get tricky. What's the normal strain in rods 1 if there is a 132-inch gap in the connections between the rigid bar and rods 1 at joints A and C before the load is applied? Okay? Now I'm going to go ahead and tell you that if there is a gap in the connections, it means that even if this guy has stretched 1/32 of an inch, these guys haven't even felt it yet because of that little gap right there. It's kind of like if this is what the bolt is in, and initially it's right here, and it's able to move down to this far before it even begins to pull on that rod. That rod doesn't even feel it as it's moving within the bolt hole. Now this is really exaggerated, but that's what the little gap is going to do. This is also incredibly dangerous because this is going to increase the stress on this bar quite a bit until it stretches that much. If that little gap is too much, it might actually cause the bar in the middle to fail and get people killed. So gaps are dangerous. Make sure that it doesn't cause issues. There we go. Now I can erase. Okay, and then we're going to do a second case where the normal strain in rods 1 is what we want to calculate if there is a 1/32 inch gap right here. So we did it for A and C first, do it for B second. Now I've given you kind of a little key there, but in the end it is still difficult to understand. So I want you to try this on your own, especially part A. I mean, that one's something you should be able to do. But try this on your own and then see if you can do parts B and C. Okay? If you can't, that's completely fine. So I'm going to give you 3 seconds to do it. You can use the power of pausing your video if you wish, or just try to blow through it in 3 seconds. And then come back here and we'll go through the rest together. So 3, 2, 1, and you're back. So let's try it out together and see how it goes. Okay. First off, for part A, it's not too terrible. Now, for the normal strain in rod 2 and its length, we can calculate the deformation. I might be wondering, like, why do we need the deformation? We want the strain in the other rods. Well, we don't actually know what the strain in those rods is. We also don't know how far they've deformed. However, they are all connected to that rigid bar. And so if bar 2 stretches this much, then the other 2 bars are also going to have to stretch that much too. So therefore, they're going to have to move this much downward along with that second bar. It'll look something like, oh, I don't have it here, but I have pictures later. So by symmetry, that means that those bars on the side, they have to stretch the exact same amount as the bar in the middle. And so their elongation is going to be equal to the elongation of bar 2. Now this is only the case right here. When we have those gaps, things are going to change. And so what we do is we take their elongation, we put it over their original length, which is far longer, and we can get their strain, which is going to be 623 microstrains. 623 microstrains. I forgot to put that in there, so if you can catch me, if this is still in the PowerPoint, you'll have to fix that. And if you catch it before I correct it, you'll get some extra credit. Okay. Now, in the second case, well, we realize that the ones in the middle or the ones on the sides are the ones that have a gap, but the connection at B is perfect. So we're still going to be moving the exact same amount downward. Also, the bar has to remain horizontal as it deflects downward because of symmetry. the lines on the sides are exactly the same. So they have to go down at exactly the same rate. Therefore, the deflection downward of joints A and C is still equal to 0.0810. Now this is why we brought in this strange term here. Like, what was this from before? I didn't go ahead and describe it because I wanted to tell you that is just the deflection of the joint. It's not necessarily connected to this because the joint can move and this bar won't stretch at all if it's loosely connected. Like, for example, okay, here am I in some larger bar, okay? This is the bolt that's attached to your rod, which is connecting somewhere in the middle. And even if this entire bar moves downward, well, that doesn't matter because all it does is it moves downward while that bolt in the middle just moves up a little bit. The joint has moved. The joint has moved. The bolt has not necessarily moved at all yet because the bar hasn't even been touched. So that's why you have to worry about this. This is why we're going to bring in these things called deflection rather than just going straight to elongation because they're going to be different right now. Deflection is going to be one thing, but because of that loose connection, it's going to be different. Now, because we have that 1/32 inch gap, that first 1/32 inch of deflection doesn't actually stretch rod 1. It just closes the gap. Therefore, if we want to figure out how much it has deflected, we're going to have to subtract off that gap, and that's the actual deflection of the bars on the side, as you can see here. This one in the middle, it's firmly attached, so as it deflects, it elongates. These two, they've got that loose connection, and therefore as they get deflected downward, they don't elongate at first, and then they do. So we subtract off 32nd of an inch, and we get that the elongation for the bars on the side is 0.04975. And therefore we can figure out the strain, which is fairly small. And once again, that should be micro strains right there. Micro strains. I'll have that corrected by the time you get to the PowerPoints. Okay, now we're going to do it where the gap is now at joint B. Now the gap is at joint B. So we know its deformation has to be this because we know what its strain is. However, we also know that the first 1/32 of an inch of deflection, when we move that rigid bar down, isn't actually stretching that second bar. So if we're going to elongate by that one, we have to go actually further deflect it down than 0.081 inches. As you can see right here. So this is the deflection that this is the deformation that we know about. That's 0.0810 inches. But to get that, we have to go 1/32 of an inch further because it doesn't deflect at first, or sorry, it doesn't deform at first. It's got this little wiggle room that does nothing. So we move down 1/32 of an inch and we haven't even started stretching this. And since this is what we know how much this stretches at the end, we know we have to go even further. This is where things get really, really dangerous because now we're stretching both of these really long. I mean, all these gaps are dangerous. Either this one is stretching a lot more or these are stretching a lot more because of that gap. So be very, very careful with how things are connected. Okay, and so what we get from this is that its deflection is 0.11225 inches. And we'll also know that for these 2 points, the deflection is going to equal the deformation because they are perfectly connected. And so with that, we can then calculate the normal strain again. Once again, I can't believe I missed this so many times. Well, I missed it one place because I missed it all. So it would be 0.11225 all over the original length, which is very long for the side bars. That's going to be 863 micro strains, or micro inches per inch. This is just to tell you what the original units were. It doesn't actually matter because obviously inch divided by inch would cancel out. Okay, so we have finished this problem, and what we introduced this time was deflection. That's talking about things are usually connected at joints. Like if you look at a bridge, always connected at joints. And sometimes we have gaps in how those connections work. Okay, there is a bolt holding these together, but it can move around before any sort of deformation happens to the bar that it's attached to. So this is very dangerous because it changes how much strain different components of your design are feeling. So you need to make sure that you take this into account so that it doesn't cause it to fail prematurely. Well, I hope this helped you. And I'll see you all next time as we do another fairly difficult problem. But this next time, we're not going to have that fun symmetry because we're going to actually have a bar where it moves like this rather than just going straight down. It's going to be fun. I'll see you all soon. Have a wonderful day. Bye-bye.